This is Note-Taking Guide 2.6. We're going to talk about what we can do when we cannot factor. Just a reminder here that when we talk about complex numbers, there's a real and imaginary part. Real is like a -1 or a 3 or a positive 1/2. All of those are real numbers. Imaginary numbers are numbers that have the I on them, like 5i or -3i. The I stands for the imaginary part. Just a couple of reminders of the rules. It's if you have the square root of like a -25, your answers to that would be plus or minus 5i, because the 25 comes out as 5, and the I comes from the negative underneath the radical. So our rules say anytime we have a negative underneath the radical, we're going to put an I on our answer. And then the other rule says anytime we see an I squared, it will be equal to -1. So we're going to use those rules as we go throughout today's note-taking guide. Just a reminder again that rational numbers can be written as fractions, and irrational numbers cannot be written as fractions. Okay? Alright, and then just another reminder about the fundamental theorem of algebra. It says if we have n as our degree, it means we have n roots. This could include complex roots, real roots, repeating roots, any kind of roots. So what are we going to do when the polynomial is not factorable? We're going to do something called the quadratic formula, or we're just going to solve it if we can. So this first problem right here gives us the factor of a -2, and it asks us to find the other zeros of the function. So we're going to continue to do what we've been doing with our synthetic division. We're going to take our coefficients from up here on our variables, and we're going to do synthetic division. So drop the 1 down, multiply by -2, add straight down, multiply by the corner, add straight down, multiply by the corner. I get a remainder of 0. So my equation right here, because I had a power 3, I'm going to start with a power of 2. I have x squared plus 2x minus 5. Now this won't actually factor. I cannot find numbers that will multiply to a -5 and add to a positive 2. So what I need to do is use the quadratic formula. The quadratic formula is that formula that says x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So what I'm going to do is identify my a, my b, and my c and substitute it into that formula. My a comes from the coefficient in front of the squared term, so in this case my a is 1. My b comes from the number in front of my linear term, my x term, and my c comes from the constant right here. So I'm just going to substitute them into my formula now. X is equal to the opposite of b. Well, because b is 2, the opposite would be -2, plus or minus the square root of b squared. 2 squared would be 4, minus 4 times a is 1, times c, which is a -5, all over 2 times a, 2 times 1. I'm going to simplify this that's on the top. This would become a positive 24, because a -4 times 1 times -5 would be a positive 20, and positive 20 plus 4 would be a positive 24. So I'll have a -2 plus or minus the square root of 24 over 2. Then I'm going to simplify that 24 underneath the radical. When I do that, I get -2 plus or minus 2 square roots of 6, and it's still over 2. And then I'm just going to simplify one more time, because here, here, and here is all divisible by 2. So I'm going to divide by 2. I'll have a -1 plus or minus the square root of 6 over 1 for my answer. And that over 1 right there doesn't have to be shown. So my answer is -1 plus or minus 6. So I actually have 3 answers here. I have 2 answers right here, and they gave me my first answer up here at the top, and I know I was looking for 3 answers because of my power of 3. This problem goes exactly the same way. I'm going to put 4 up in the corner. I'm going to do synthetic division with my coefficients of 1, -4, -7, 28. So really quickly I'm going to synthetic divide. I always love it when I get zeros here, because it kind of makes a nice equation happen. So when I rewrite this equation, it's a power of 2. I'll have x squared plus 0x, which I don't need to show, minus 7 equals 0. Now we could totally put this through the quadratic formula, but we don't have to because I'm able to just solve this. If I solve this by isolating the variable, I can just add the 7 over to the other side, and I get x squared equals 7. To get the squared off the x, I'm going to square root both sides. So I get x equals plus or minus 7. So if I were going to list my answers out, I'd have x equals a positive 7. Oh, I forgot my square root, sorry. The square root of 7. I'd have x equals the negative square root of 7 from separating these right here. And then my last answer would be x equals 4 from the answer that they gave me up at the top. So just a reminder of the quadratic formula. It's down on the bottom of your paper, so make sure that you refer to that if you need it. So anytime we have irrational solutions, we also have its conjugate pair. So if you noticed over here when we had the square root of 7 for our answer, we also had the negative square root of 7. So we have it and its conjugate pair. So if we have a plus square root of b for our answer, we'll have also a minus the square root of b. If we have 1 plus the square root of 2, we will also have 1 minus the square root of 2. If we have the square root of 10, we also have the negative square root of 10. And if we have 2 minus the square root of 6, we also have 2 plus the square root of 6. Those are called conjugate pairs. That will always happen. If you have one of those solutions, you will automatically have the second one. So right here where it says write a polynomial equation with integer coefficients that has this root and that root, find the two additional roots, and then what's the lowest degree this polynomial could be. Well, the additional root from here would be 1 minus the square root of 3 because of its conjugate pair. And then the conjugate pair of a negative square root of 11 would be positive square root of 11. So we know that we have 1, 2, 3, 4 solutions no matter what. So the smallest that the degree could be would be a degree of 4. Okay, same thing on this next one. It asks us to find two additional roots given that this is one of our roots and this is one of our roots. So we're just going to list the conjugate pairs. The conjugate pair of 2 minus the square root of 7 is 2 plus the square root of 7. And the conjugate pair of the square root of 5 would be negative square root of 5. So those are our two additional solutions. All right, what are the zeros of this polynomial function? Well, if you remember, we talked about the zeros being where our graph touches or crosses the x-axis, and we know it touches or crosses there at 3. So if I know that one of my solutions is 3, I can do synthetic division and see if I can find my other solutions. So my coefficients come from here, 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 and here, and then I just do my synthetic division with 3 in the corner. Drop the 1 down, multiply to get 3, add to be 0. I love the 0 because that means I don't have to do the quadratic formula to solve it. Add straight down here, multiply, get 0 again. If I rewrite this equation, it's x squared plus 1 equals 0. And I can solve this by subtracting the 1 over to the other side. Square rooting. And then this is just a reminder that every time I square root a negative 1, I get plus or minus I. Because the square root of a negative 1 is I. So 3 solutions here. My first one was 3. My second solution is a positive I. And my last solution is a negative I. Same thing again here. We're going to find our solutions. This time we have 2 that they said is a function, factor of our function. So we're going to grab our coefficients again and do synthetic division. Drop the 1 down, multiply by 2, add straight down, multiply, add, multiply. And again, I love this one because I have that 0 right here, which means I just have x squared plus 9. And then I can set that equal to 0 and solve it. I'm going to subtract the 9 over. So I get x squared equals negative 9. Then I'm just going to square root both sides. Anytime I square root a negative number, I'm going to go ahead and throw an I on my answer, and then square root the number that's in the box or in the square root, and the square root of 9 is 3. So I have two answers here. I have a positive 3i, I have a negative 3i, and then my answer up here is 2 for my 3 solutions for what x is going to be. So again, just like with our irrational solutions, our conjugate pairs happen with our imaginary solutions also. So if I have A plus BI as a solution, then I also have A minus BI. If I have 1 plus 2i, I also have 1 minus 2i. If I have 7i, I also have a negative 7i. And if I have 2 minus 9i, I also have 2 plus 9i. So again, all complex solutions have their conjugates with them also. So it says if a polynomial equation with real coefficients has 3i and negative 2 plus I among its roots, then what are the other roots that it must have? Well, it must have a negative 3i, and it must have negative 2 minus I. So if you notice again, the real part stays the same and only the imaginary number changes when we're talking about the conjugate. Same thing on this one. A polynomial with integer coefficients has these roots. Find two other roots. Well, if it has 3 minus I, it also has 3 plus I. And if it has 2i, it also has a negative 2i. This next one says it's the super bonus challenge problem. But really, we're just going to write the opposites again. We have 2 plus 5i. We have negative 3 plus 2i. We have 1 plus the square root of 2, and we have positive root of 7. So if we were going to talk about the degree of this one, the minimal degree that would have would be 8. So we know that it has at least 8 solutions there. All right, this one says find a third degree polynomial equation with rational coefficients that has roots of 7 and negative 3i. Well, I know that if it has a root at 7, I'm going to put x minus 7 back in parentheses and multiply it out. If it has a root of x minus 3i, I'm going to have x plus 3i. And then because of this right here, I also know I have its conjugate pair, which would be a plus 3i, which is going to be put back in as a minus 3i. So I really am just going to multiply this out now. And I would always multiply these conjugate pairs first because special things will happen with them. We'll have some canceling happen. So we'll have x squared minus 3xi plus 3xi minus 9i squared. I still have that x minus 7 in front, but let's see what happens here. Those middle terms cancel really nicely. And then right here, this minus 9i squared would be a minus 9 times a negative 1 because of that rule I told you on that front page that a negative 1 is what I squared is. So every time I see an I squared, I get to replace it with a negative 1. So that turns into x squared plus 9. Then I just have to multiply it through by the x minus 7 to be done. I get x cubed plus 9x minus 7x squared minus 63. Now I'm running out of space to rewrite this, but I really should have that from highest power to lowest power, so I'm going to see if I can fit that in right here and write that from highest power to lowest power. All right, one more example of this kind here. We have a root of 3 and a root of 2i. It's a degree of 3, which means I know I have a root at x minus 3 as far as the factor goes. I have a root at x minus 2i, and then because I have the positive 2i, I also have a negative 2i as a root, so I'll have x plus 2i as my last root here. I'm going to multiply those out. I will always do this first, so I'm going to get x squared plus 2xi minus 2xi, and then minus 4i squared. Middle terms cancel. I get x squared plus 4 because that I squared down there changes that to a negative 1. So negative 1 times negative 4 is a positive 4. Then I just multiply here. I have x cubed. I'm going to leave a little spot here because I get plus 4x, and I know I'm going to have an x cubed here. So a minus 3x squared and a minus 12 for my solution.